We're going to start going through the detailed discussion now of various topics that we've talked about so far. These are in relation to this iteration loop of design-oriented analysis. Most of the techniques are to do with the analysis part of it, but of course it's going to be a very special kind of analysis, namely design-oriented analysis. The first technique we'll discuss is lowering the entropy of an expression. And the example is the one that I showed briefly already. Taking one step further back at the moment, the circuit we're talking about is the basic common emitter bipolar transistor, so-called linear amplifier stage. The picture on the left shows the equivalent circuit model of the transistor, the beta collector current generator, the RE base emitter junction slope resistance. That's actually representing the nonlinear exponential current voltage characteristic of the base emitter junction. It's also the reason why this is known as a small signal AC model, because the transistor is basically a nonlinear device. The principal nonlinearity is that base emitter junction, which is an exponential. And as in all nonlinear devices, we try to find a linearized model of it so we can apply all the standard linear analysis techniques. You notice practically all the techniques we get taught are linear analysis techniques. They're the only easy ones. Nonlinear systems are much more complicated. In fact, if you've taken a course in nonlinear systems, it was probably a graduate level course. You notice very quickly a lot of foreign names start cropping up. And if you look at the end of the paper, there's an obscure expression with a lot of weird symbols, and it's a high entropy expression. There's not very much you seem to be able to do with it. In other words, nonlinear systems usually have to be treated on an individual basis. There's not much you can say about them in general. That's the real motivation for whenever you possibly can, you try to linearize something. And this is the result of linearizing the exponential characteristic of the base emitter junction of the transistor. The value of RE is different for different DC operating points, because it's the slope resistance of the exponential, which is different at different places on the exponential, represented by the operating point. You remember the simple formula for the value of RE. It's equal to the thermal voltage, that's 25 millivolts at room temperature, divided by the DC operating emitter current. So at 1 milliamp of DC current, the value of that resistance is 25 millivolts divided by 1 milliamp, or 25 ohms, inversely proportional to the DC operating current. So that's about the simplest possible model you could use to represent the bipolar transistor. Outside of that, RB represents the bias divider, actually coming from R1 from the supply to the base, and R2 to ground, but since the power supply is the same as AC ground, those two resistors R1 and R2 can be put in parallel immediately. We have a coupling capacitor to keep the DC bias condition separate from the source, and we have a bias stabilizing resistor R in series with the emitter. That's how we get a stable operating point, even though the beta of the transistor may vary a lot. And often that bias stabilizing resistor is bypassed by another capacitor to remove it from the AC model. And that's the picture on the right-hand side. That's the small signal AC model, and it's a mid-band model because both the coupling and the bypass capacitors have been taken to be AC shorts. So this is a model valid for frequencies where those two elements are AC shorts. It is still called mid-band because high-frequency capacitors are left out altogether. Principal high-frequency capacitor is the collector base internal junction capacitance of the transistor. Also, there is an internal capacitor known as the diffusion capacitance, which really is across the RE. As we go down the list of these techniques, we will restore these capacitors one by one. First the bypass capacitor, then the coupling capacitor, and finally the collector base capacitor for the high frequency response. They will all be used or are restored as applications of the extra element theorem. For the time being, we're going to be dealing just with the midband model, because first we want to know what the midband gain is and see how we can put it into the form of a low entropy expression. So the first thing we do with this AC model now, by the standard approach, which is using Kirchhoff's laws, then we would identify 3 loop currents for that circuit model, which means we would write 3 simultaneous equations representing Kirchhoff's law for each of those current loops. The problem in this case is actually a little simpler, because the third loop current is a fixed multiple of the second one because of the properties of the equivalent circuit model in this particular example, because the third loop current is beta times the second loop current. So already this is simplified down to only a 2 independent loop current model. So the standard way of doing the analysis is you write the 2 loop expressions, Kirchhoff's laws for each loop, for which the solution for the base current is a ratio of 2 determinants. One more step now, multiply the IB by beta by RL, gives you finally the midband gain of the circuit. Solving the ratio of 2 determinants gives you this intermediate expression, and then substituting into the final expression, multiplying by beta RL, gives you the final result. This is the example we had first in the introduction. The answer is just the way it comes out of the brute force algebra. No attempt at arranging anything, that's just the way it comes out. And of course, it's the ratio of sums of products of the circuit elements. This was a 2-loop model, so we get sums of products 2 at a time. If it had been a real 3-loop circuit, we would get sums of products 3 at a time. So it's easy to see how the algebra escalates very rapidly when you get to more complicated circuits. The point about this result is it's high entropy, because there's nothing you can do with it except plug numbers in, and if you don't like the answer, you don't get any guidance as to how to rearrange it. So let's see what we can do with that result to make it low entropy. That is, how we can squeeze more information out of it. Well, here's the same answer again. First thing you notice about this is that we have a common factor in the first 2 terms in the denominator, 1 plus beta. So we can bring out 1 plus beta times RE. That leaves RS plus RB from those same 2 terms. Having done that, you can see that if we have an RB in the numerator as well, if we bring out RB from the numerator and RS plus RB from the denominator, we get a ratio of resistances which has a direct physical interpretation, because that is the resistive divider that the source looks into. RB over RS plus RB is simply a divider ratio whose physical origin is obvious from the circuit. So it's a convenient factor to have in front. Now, if I bring out the RS plus RB from the first 2 terms, then of course I have to divide it into the third term of the denominator. So I get product over sum. But that should be identified as parallel combination. So write it that way. Notice already you see an aspect of design being the reverse of analysis. You observe product over sum and you replace it by the parallel notation, which is the opposite direction from what you normally do. But this is how you get the benefit of the low entropy result. So now we have a denominator which illustrates that parallel combination. One more thing we can notice about this result is we have a beta in the numerator and we have a 1 plus beta in the denominator. Now beta is a large number. At least it is in any transistor that you're not going to throw away. But it's also one of the most variable parameters. It's poorly controlled. In fact, it's a second order parameter of the device. So if I bring out front beta over 1 plus beta from this expression and call it alpha, which is the standard symbol for it, alpha is very close to 1 regardless of the value of beta as long as beta is large, which it's going to be. So numerically, alpha can simply be taken as 1. What has happened now is I have to divide 1 plus beta into the second term of the denominator, which gives this final result. This is the expression that in the introduction I showed directly after the first one, and I claimed that this was a low entropy expression. And I mentioned 1 or 2 points about it already. Now we can see there are other values to that result, because you can observe several other things. First, this resistive divider factor in front is identified as the voltage divider directly from the source. We know that factor is less than 1. So whatever value of gain we have to design into the specification, we know that the second factor in the result has to be bigger than 1 sufficiently to overcome the loss of the first factor. So that's useful information. Next thing we notice about the result is we have these series parallel combinations of resistances. That's useful information because we know series combinations are dominated by the biggest one, parallel ones are dominated by the smallest one. So we know what the relative importance is of these various resistances in the answer. That's the one I mentioned in the introduction. But there's still a third one. The relative values of these two terms in the denominator determine the sensitivity of the gain of the total stage in relationship to the variation of the parameter beta, which is the most variable parameter in the whole circuit. As an example, suppose for a given set of trial values, term number 1 and term number 2 in this denominator are equal. And suppose we have to allow for beta to vary plus or minus 20% from the data sheet nominal value. What is the resulting variation of the gain of the stage? That's intended as a question for you to answer. 10%, right. The variation of beta is diluted by a factor of 2 in the result if those two terms are initially the same value. If they're not the same value, the dilution factor is different, but it's easy to find out what it is. That's another useful thing to know when it comes time to choose or to change the values you have in the circuit. So there are 3 useful things that have come out of that low entropy expression, which are not obvious from the original high entropy expression. Those 3 additional pieces of information, therefore, amount to 3 other equations that you're not going to get. They're not in the form of equalities, but they're in the form of at least inequalities, and certainly enough information to help you to choose optimum values for more of the circuit elements. So that's a very simple illustration of the basic way of getting more than one piece of information out of one equation. Okay, now just to summarize that. Disadvantages of the conventional analysis method. You get no direct physical interpretation of the answer. It simply comes out of the algebra, which means it obscures the relationships as to how element values affect the result. In turn, that makes it difficult to use for design. given the AM, which is the spec, that's the answer, how do you choose element values? And finally, the purely algebraic derivation increases the likelihood of you making mistakes, because you're divorced from the original circuit. All you do is pushing symbols. On the other hand, the advantages are simply the opposite. For the low entropy form of the result, you do get the direct physical interpretation of the answer, so you can see how the elements affect it. Makes it much easier to use for design, and that's the whole purpose. The final one I've left as a question mark, because at the moment you might say, well, I did some more algebra to push the first answer into the low entropy one, and so there's even more chance of making algebraic mistakes. This leads to the next question, though. Rather than letting the entropy rise by doing blind algebra, and then at the end of it all, trying to put the mental effort in to lower the entropy, why not try to keep the entropy low all the way by using a different method of analysis, which is really what design-oriented analysis is all about. See, not only do we spend 90% of our student days doing analysis and only 10% doing design, but the design is tacked on at the end. But actually, it ought to be part of the objective all the way from the beginning of the analysis, which is why design-oriented analysis is the only useful thing to do. So it's easier and better to keep the entropy low from the very beginning. Let's see how we might do that. Go back to the circuit model. One thing we can do to manipulate this circuit is to separate this RE from being part of both the part of the input loop and the output. We can reflect that RE into the input. The only difference in this model is that the RE is being taken away from the emitter, and instead it's being placed in series with the base. And at the same time, its value has been multiplied by 1 plus beta. Now, that's a circuit manipulation trick. And the reason that it works is that I've maintained the same voltage drop from base to ground in this model as we had in the original one. Because the current flowing through this resistance is IB, causing a voltage drop of 1 plus beta RE times IB. And that is the same as the voltage drop in the previous model, because I have a current equal to the emitter current, IE, times RE, but the emitter current is 1 plus beta times IB, because the emitter current is the sum of the base and the collector current, which is 1 plus beta IB. So this is an equivalent circuit, because I get the same answer for the voltage drop base to ground in this model as I do in this one. Now you might say it's not equivalent as far as the output circuit is concerned, but it is, because this is an ideal current generator that drives a given current regardless of the voltage across it. So it doesn't matter what the voltage at the bottom end of that generator is as far as finding the output voltage is concerned. So this is an equivalent circuit model because it gives me the right answer for the voltage gain. That's an interesting point about equivalent circuits. In general, that's all an equivalent circuit has to do: give you the right answer. See, it's no more complicated than that. That's all it has to do. And that's all you make it do. It's all that's required. So in this particular case, these are equivalent circuits because they both give you the right answer. So the only question remaining is, why do I bother to make this change? The reason is that it makes it a little more obvious on the circuit diagram now how you can separate the input part of the circuit from the output part and break the analysis down into two separate pieces. Bearing in mind that that's always a good objective, to break one heap of algebra down into smaller pieces. So when you manipulate the circuit like this, it's obvious now that you've separated it into two pieces. So what do we do from here on? Incidentally, this process you could call reflecting the emitter impedance into the base. And the rule is, to do that reflection, you multiply the value of the impedance by 1 plus beta. And that is a consequence of the property of the transistor model, that the sum of the collector and the base currents always equals the emitter current. And another way to say that, which we'll be using a number of times, is this means that all three terminal currents of the transistor always have fixed ratios. Collector to base is always beta, emitter to base is always 1 plus beta, collector to emitter is always beta over 1 plus beta, which is alpha. Fixed ratios. And the special case of that is if one of the currents is 0. All of them must be 0. We'll use that when we get to the extra element theorem. So it's that property that makes this reflection process possible. Okay, now let's make use of the fact that we've now separated the input and the output parts of the circuit. Now we want to find the base current as a function of the source voltage V1. That can be broken down into two steps also. Intermediate step is, let's find IB as a function of I1, which is the input current. Notice that the I1 is looking into a current divider. You're familiar with voltage dividers, but you need to be equally familiar with current dividers. This is a current divider. Some of the input current becomes IB, the rest of it goes down the RB. It takes only one application of Ohm's law to arrive at this very simple result, which is the ratio of the current in one branch to the total current in two branches is the ratio of the opposite branch impedance to the sum of the two branch impedances. There's only one line missing of Ohm's law to get that. So in this particular case, the ratio of IB to I1 is the opposite branch impedance, which is RB, to the sum of the branch impedances, which is RB plus 1 plus beta RE. So that's where that fraction comes from. I've done it this way in order to introduce that as another little general technique that you can use in lots of other places. Okay, having got that, we now want to know what I1 is as a function of V1. So that's V1 divided by the total impedance seen by V1, which is RS plus RB in parallel with 1 plus beta RE. Now, don't multiply that out. That's simply raising entropy unnecessarily. It's already in low entropy form. Leave it that way. Don't waste that information. Okay, the final equation is V2 is beta IB times RL, so all you do is multiply those three equations together, and that gives you this result. So this is a low entropy result because all of the impedances are either in terms of ratios or series parallel combinations. So it's easy to see how they come from the circuit. This factor in front immediately represents this current divider property. Again, it's a ratio which is always less than 1, so the other one will have to make up for it. Now, that's only one way to get an answer. Notice this is not the same low entropy result as we had before. Here's another way, which does give the same low entropy result as we had in the first case. First thing I've done this time now is, if I still go back to the original circuit, the first step this time is to absorb the RS and the RB into a Thevenin equivalent by applying Thevenin's theorem. which immediately gives you this picture. Here's the Thevenin equivalent source, which contains the divider ratio. Here's the Thevenin equivalent impedance, gives you RS parallel RB. Now, we can do this reflection process backwards. We can reflect the base impedance into the emitter by dividing its value by 1 plus beta. It's using the same property, the fixed ratio between the base and the emitter currents. And it works because both models give you the right answer. The right answer in this case is the right sum of the voltage drops around that loop. Because the voltage drop across the base resistance is RS parallel RB times IB from this model. From the other model, the voltage drop is the resistance RS parallel RB over 1 plus beta times the emitter current. But the emitter current is much bigger than the base current, and that cancels the 1 plus beta factor, and you get the right answer. So again, these are equivalent circuits in that sense. So the second question again is, why is it worth bothering to make the change? This time, the reason for doing it is that the Thevenin equivalent source now appears directly across those two resistors in series. So immediately I can write the emitter current. The emitter current is Vs divided by the sum of those two resistors. And that's almost all you have to do to find the answer. Because the emitter current multiplied by alpha is the collector current, multiply that by RL and you get V2, and that's the result you're looking for, V2 as a function of Vs, but we already know Vs as a function of V1, so that gives you the divider factor in front. So this is the same low entropy expression we had before. And notice that having done it this way, you never have to do this again for any other common emitter amplifier stage if you simply remember this result in words. The voltage gain of the basic common emitter amplifier stage is the total collector load, which is a generalization of the RL, because obviously whatever network there may be up here, it's just the total impedance that multiplies this current generator to give you the V2. So the total collector load, whatever it is what you put in the numerator, and what you put in the emitter is the total emitter load, including any reflected base impedance. So whatever other impedance there may be out here, you could reflect it in the same way, and the denominator is simply the series sum of all those resistors after you've accounted for all the reflected ones. The alpha is in front simply because of the ratio of the collector to the emitter current. And that's all you need in the answer. So if you just remember that, which is easy to do because it's directly related to how the circuit is working, then you can write this answer down for every common emitter amplifier stage. But the derivation is very simple, does not involve simultaneous solution of equations, and the answer is automatically in factored pole zero form, because that's how it got built. Well, we've seen something else now to do with the generalization of this. These are two different versions of the same answer. I can't get them both in the picture at the same time. Well, anyway, you can see in the note. This was the first version. This is the second one of the present derivation. They look different, but of course they are the same. So you see now that a high entropy expression can be shown in many different forms, but they're all useless. Low entropy expressions are also available in many different forms. The point about that is you have the choice. It's a matter of which one is most useful for a particular application. And to get the maximum information out of it, you choose the one which exposes the things most directly related to the answer that you're looking for. And if you want to look for a different answer, a different low entropy version may be appropriate. Just as an example, looking at these two. This expression is already useful for telling you 3 more things. We talked about them already. Divider ratio in front, series parallel combination of resistors, sensitivity to beta. Those are the 3 direct pieces of information you get out of this one. That's fine. When might the other one be useful? This one obviously is not so good for looking at the sensitivity with respect to beta. Not good at all. See, the beta is in 3 different places. This one is good for finding the input impedance of the circuit. Remember that theorem? Well, you probably don't remember it yet because you haven't tried to use it. But remember, all it involves is using the voltage gain and taking a limit with respect to the source impedance. RS is the source impedance, and it's in the expression for the gain. In this version, in this low entropy version, it's in only one place. It makes it easy to use that theorem to find the limit. Whereas, if you tried to use the theorem for this expression, the RS is buried in 2 different places. So it takes more work to apply the theorem. So, again, there's some simple examples of how you have a choice of which low entropy version to get. Different ones may be better for calculating different things. The main thing is, remember that you have the power to get different versions that may be more helpful. Okay, to pursue this through to the end now, here's a typical set of numbers. And the only noteworthy point is the value of the RE, which I mentioned. The formula for it is the thermal voltage divided by the emitter DC current, which in this particular case is 0.7 milliamps, so the RE comes to 36 ohms. So here's the substitution of those values into one of the low entropy results that we got. And here's the intermediate computation. And the reason I'm showing this is to emphasize that it's worthwhile writing down this intermediate computation step. In spite of the fact that obviously you could do all this in one sequence of key punches on your pocket calculator, and you could get the answer. But if you do that, you're wasting this useful information to do with the relative importance of different elements. So in this particular case, when you work out this denominator, the RE is 36 ohms. The other term turns out to be 39 ohms. So they are just about equal. So for this example, this means that the sensitivity to variations of beta is diluted by about a factor of 2 to 1. And you see, if you simply plugged the numbers in and got the answer, you'd have missed that. So this is making use of the low entropy analytic version. Other uses of it, of course, would be how to approximate by leaving out terms altogether. If in this intermediate step it's obvious that they're negligible. Okay, so here's a couple of sentences about low entropy expressions. The results for the AM by the 2 methods, of course, have to be the same, but the formats are different. Different groupings, different low entropy versions. Any grouping has more useful information than the high entropy version in which everything is just all multiplied out. One of the generalizations that we've developed as part of this is that you can treat current dividers at the same basic simplicity as voltage dividers, which you can use in all sorts of different places. That one I mentioned already. Now here's another very useful one that I haven't explicitly emphasized. We've done the example. I said every time you use Thevenin's theorem, the circuit got simpler. It got simpler by reducing the total number of loops by 1. But there's a dual to Thevenin's theorem, which is Norton's theorem. It says you can replace any linear part of the network by a current generator in parallel with an impedance, and you remember the rule for doing that. Now, I don't know how often you use Thevenin's and Norton's theorems when you're doing your analysis. I would guess they're about the only theorems you ever use much, but maybe you could use them to advantage even more. If you simply remember that the value of the theorems is every time you use Thevenin's theorem, you get rid of one loop. Every time you use Norton's theorem, you get rid of one node. And that means that if you start with a multiple loop, multiple node circuit, you can use those theorems in succession, and you can gradually reduce the complexity down maybe to a single loop. Every time you remove a loop or a node, you are effectively eliminating one of the original set of simultaneous equations. And that's an obvious benefit. If you can reduce it down to one loop, you can write the answer in one line. So that's the real value of those two theorems. It's really a way of doing the algebra on the circuit diagram. There's a bonus on top of all that. Not only do you reduce the algebra, maybe down to zero, if you can write the answer in one line, but you automatically get the answer in low entropy form. Because as you reduce the circuit by use of the theorems, the element values gradually get more complicated, but they get more complicated in the right way. Series parallel combinations and ratios. So keeping the entropy low is something that happens automatically without you even having to think about it. That's the best value of all. So that's even more powerful than the current and voltage divider similarity. So here's that same example I had right at the beginning. So the net result is simultaneous solution of multiple loop or node equations is replaced by the sequential, simple, semi-graphical steps of doing the algebra on the circuit diagram. Element values in the successively reduced models automatically appear in the low entropy format, which facilitates the trade-offs. And you have less likelihood of making algebraic mistakes. That replaces the question mark we had in the previous summary. Because now, instead of doing extra algebra at the end to force the algebra back into a low entropy result, instead you actually do less algebra. Maybe none at all, which is the best of all. So that's very simple and basic examples of what low entropy expressions are about. And you may say this is all so trivial that it's not even worth bothering about, but the important thing is this is the entry to making complicated problems simple. This is how you prevent the algebra from mushrooming into these impossible messes. You don't let it happen right from the start. You don't try to recover a simple answer out of a complicated one. You keep it simple all the way. That's the only way to handle it. And you've got to start from a simple model to do that also. Then you can add things to the model as they become necessary.